So not everyone will be familiar with critical phenomena, and so I'm going to try to give a little bit of an introduction to that in this first lecture today. And I want also to focus on a very concrete problem, because I think it's easier to understand what's going on if we have a specific problem in mind. What I'll be talking about is part of a long research project which has appeared in several papers over the last 4 years with David Brydges and Roland Bauerschmidt, who are here, also with Ben Wallace and Martin Lohman and Alex Tomberg. I don't have any notes on the web or anything like that, but with Roland and David, we finished a book a couple of months ago, which is on my web page, that touches on the topics in great detail that I'm going to be discussing today. And I've also written a kind of Reader's Digest version, which is on my web page since last month. And so that's the kind of thing that belongs in a doctor's waiting room or something like that, so you can read it calmly you don't need a pencil for that one. Right, so critical phenomena encompasses many features that have been very important in mathematics over the last 30 years, especially percolation, Ising model, spin systems of various kinds, self-avoiding walks. They all kind of fit into the same category. And one of the interesting features is the dimension dependence of these of the critical behavior of these models. And in 2 dimensions, there's been quite a lot of progress in the mathematical side since the turn of the century with the invention of the Schramm-Loewener evolution, SLE, which has provided a mathematical framework for the understanding of all kinds of problems in critical phenomena in the 2-dimensional setting. There's still lots of open problems there for us to work on, but there has been a lot of progress, and the 2-dimensional case is special. In 3 dimensions, from a mathematical point of view, we know almost nothing, I would say, about critical phenomena. I'd like to give you an example. It's only been proved in the last few years that the magnetization of the Ising model vanishes at the critical as the external field goes to 0 at the critical point. The corresponding problem in percolation is that there's no percolation at PC, and that's still not proved in 3 dimensions. So in 3 dimensions, we're kind of in the dark. In high dimensions, there's mean field theory, which describes a lot of the phenomena, and this has been proved using various methods. Reflection positivity and the infrared bound have been successful there. The lace expansion has solved a lot of these problems. And so the situation in high dimensions is good. The borderline dimension for the spin systems like the Ising model or the 5^4 model that I'll be talking about here is dimension 4, where you're at the transition between the easy case of high dimensions and the difficult case of low dimensions. And that's what I'm going to be talking about today. So I want to focus on 2 models. In fact, I'm going to be almost entirely talking about the 5^4 model, but I'll spend a little bit of time today talking about self-avoiding walk as well. So we've already heard a lot about this. We have the lattice ZD, which we're going to approximate by a box lambda n, which I'll take to have periodic boundary conditions. So it's the discrete torus, and because there's going to be this sort of block type structure coming in, I want the side of the torus to be scaling like L to the n. L is some fixed number. In practice, we want it to be a large number, but you can think about it as 2 or 3 if you like. And n is going to be going to infinity, and that will be the thermodynamic limit in which the model extends over the entire lattice ZD. And there's a spin field, phi on lambda, which in my case is going to take values in Rn. So you're free to think about the case of n equals 1, which is the 5^4 model that's been discussed up until now. Horst was talking about a complex field, so that corresponds to n equals 2, but you can take n equals 3 or any other positive integer value that you like. So phi then is just an element of the space Rn to the lambda. Oh, this one doesn't raise, right. And there's an expectation which is associated to this. So the expectation of a function f from Rn to the lambda into R is defined as follows. So I'll write it like this. Typically depends on a lot of parameters, which I may or may not make explicit. There's a normalization constant, the partition function, and then there's a big integral over Rn to the lambda of f of phi against some measure. And the measure has two parts to it. There's a part that sort of couples different spins, sum over xy in lambda of some matrix mxy phi x phi y. I'll say some examples of what that m is. And then there's a single spin distribution, product over x in lambda of e to the minus v phi x d phi x. And that d phi x is just Lebesgue measure on Rn, and there's the product giving the Lebesgue measure over Rn to the lambda. So this here is called the single spin distribution. And I have a specific one in mind, which is the one that corresponds to the phi to the fourth model. This part here I want to take to be ferromagnetic. And what that means is that mxy should be greater than or equal to 0, less than or equal to 0, if x and y are different. So that ferromagnetic interaction has the effect of encouraging spins to have a positive dot product with each other. Right? There's two minus signs. There's a minus from the m, and there's a minus here. So this factor gives more weight to large, phi x dot phi y. So spins are encouraged to line up with each other by this factor. Now, the v that I'm particularly interested in is the one that's been discussed at length already in this conference. I'll use a slightly different, some numerical factors that are convenient to put in here. And I think I'm following the opposite convention for var phi that Anti had, but I will never have any continuous spins, so it shouldn't cause any problems. And I think nu was called r by Anti, and so on. But anyway, this is the notation that I'm going to be using. And so g you should think about as being some fixed number, which I will have to take to be small. But it's not sort of the interesting variable. The interesting variable is nu. And it can be positive or negative. And I'm particularly interested in the case when nu is negative. Because when nu is negative, this single spin distribution has a double well shape. Here's the shape. Let's draw it for the case of n equals 1. So this is v of phi x versus phi x. It has this shape like that with two wells. This is for the case of nu negative, the one that I'm interested in. And these minima are located at the square root of absolute nu over g. And the value of the minimum is minus 1/4 nu squared over g. So as nu becomes more negative, these wells become deeper and more widely separated. And this is in the exponent up there, e to the minus v in front of the Lebesgue measure. So you should sort of invert that and turn it upside down. Think of these as peaks, which are encouraging the spin to lie underneath that peak. So there's two favorite points in a way, or two favorite regions for the spin, which are near the values that correspond to the minima. The ferromagnetic factor is encouraging neighboring spins to line up with each other. Well, that is, let's think about mx as just having nearest neighbor interactions for this discussion. And so there's this tendency, if some spins are lying at this value here, for them, their neighbors, to want to lie there as well, as far as this measure is concerned. And so that effect is going to become pronounced as nu becomes more negative. And so you can imagine that there might be some phase separation and long-range order developing as nu becomes more negative, and that's the phase transition that happens at a sharp point. So the values of mu, of m, I should say, that I'm interested in, there are two for today. One is that m is minus the Laplacian, which is minus the Laplacian on lambda, because we're really talking about a finite discrete torus here. So I think you know what the Laplacian is, but it's j minus 2di, where j of xy is equal to 1 if x minus y, x and y are neighbors, and it's 0 otherwise. So it's the usual lattice Laplacian on the torus, and that's one example. It has this ferromagnetic property that I mentioned. And the second example is m is a fractional power of the minus Laplacian, which is most easily defined in terms of the Fourier transform. So if you take the Fourier transform of the Laplacian, it's a multiplication operator. You just take the alpha over 2 power of that multiplication operator. That gives you the Fourier representation of this operator. And the interesting thing about this operator is, so alpha here is a number between 0 and 2, so that this alpha over 2 really is a fraction between 0 and 1, is that it's a long-range operator. That is, that its kernel has this decay, that minus mxy decays like 1 over x minus y to the d plus alpha as x minus y goes to infinity. Of course, on the torus, x minus y can't go to infinity, but we're interested in large toruses. Anyway, this is the behavior on ZD. So this kernel does not have a finite variance. If you multiply x squared times 1 over x to the d plus alpha, that will not be summable if alpha is less than 2. So what sort of problems are we interested in here? Here are some quantities of interest. There's the 2-point function, which I'll call g0x. It depends on various parameters, which I'm making explicit now. So 0 and x are lattice points, and it's just the limit in the infinite volume of the correlation of phi 0 with phi x. So this expectation depends on various things. After a while, I'm going to stop writing all of these down. And it's useful to normalize things by 1 over the number of components. All right, so I want to think about what's happening as nu is being decreased, becoming more and more negative. These two wells become more and more pronounced. As I was trying to argue, because of this ferromagnetic interaction, the spin may prefer to lie in one well rather than the other, and that will give rise to long-range correlations. This 2-point function will decay exponentially above some critical point, and then it will, but the rate of exponential decay will go to 0 as that critical point, as nu gets more and more negative and approaches the critical point. The way that we're going to see that is in terms of the susceptibility. So the susceptibility is the infinite volume limit. I don't really want to discuss questions here about the existence of the infinite volume limit. In the theorems that I'm going to be stating, the existence is sort of part of the theorem, although there's sometimes other methods using correlation inequalities for proving the existence of the infinite volume limit. But those correlation inequalities are absent if the number of components is greater than 2. So it's the sum of the 2-point function. So what can happen is that, and what does happen, is that as nu decreases, this two-point function is decaying less and less rapidly, and this sum of these correlations is going to diverge as nu approaches some critical value nu c from above. So that's the critical point. And that susceptibility is going to be a focus of what I'll be talking about. There are various definitions of correlation length. The one that I'm able to say something about here is sometimes called the correlation length of order p. It's a kind of a pth moment of the two-point function. So p here is greater than 0, and so chi p, which depends on our parameters, is the sum over x of x to the p g0x divided by the sum over x g0x. And this will also blow up as nu approaches nu c from above. And we're interested in the rate of that divergence. A couple more quantities of interest. The pressure. The pressure is basically talking about this partition function. So that partition function will have an exponential behavior, and the exponential rate is the pressure. So P g nu n is equal to the limit as n goes to infinity of 1 over lambda times the log of p. So these are all just definitions. And a physical quantity. P on the left and on the right. Thank you. Partition function. Yes, thanks. So another quantity, and the last one that I'm going to define, is the specific heat, which I'll define as the second derivative of the pressure with respect to nu. So Ch g nu is equal to the second derivative of the pressure. And if you just differentiate underneath the limit and so on, you'll get that this is the limit as n goes to infinity of the sum over x in lambda of, and then I don't know if there's a 1 over n, there's a 1/4 of phi 0 squared phi x squared, where this is the truncated expectation that we've seen before in some other talks. It's just another notation for the covariance. So this notation means, in general, if I have two random variables f and g, it's just the covariance of those random variables. So a convenient shorthand that shows up quite a bit. So what we're interested in here today are critical exponents, which characterize the way that these quantities behave near the critical point. And so the susceptibility is going to be blowing up, and it should blow up typically like a power. And that power is called gamma. So I'm not going to be very precise here about what the approx, backslash approx means there, but it presumably is just an asymptotic, the first term in an asymptotic expansion. That there's an actual, there's an amplitude and there's an asymptotic relation there. That would be the strongest kind of statement. The correlation length blows up like another critical exponent, which unfortunately is called nu. I'll put a little bar over top of it to distinguish it from the other nu. And the two-point function at the critical point itself does not decay exponentially, but rather decays as a power. And that power is called d minus 2 plus eta. So d minus 2 would be the Gaussian behavior. The green function for the Laplacian is 1 over x to the d minus 2 for large x. And this eta is sometimes called the anomalous dimension because it's, it's sort of shifting that power, which involves the dimension. And the specific heat also has singular behavior at the critical point. It diverges possibly like 1 over nu minus nu c to the power, which I'll call alpha sub h, to distinguish it from the other alpha that we had there. So these exponents, I've presented them here for the case of the phi to the fourth model, but they have corresponding exponents in other models. For the Ising model, for self-avoiding walk, for percolation, these exponents exist also in in those contexts. And it's a very good idea to always give them the right name, gamma, nu, eta, and alpha, because they have a kind of a personality which persists from one model to the next. In particular, they obey relations, so they're not independent. This is all physics that I'm talking about now. It's part of our job as mathematicians to try to prove these sorts of statements. But they're relations, so there's a scaling relation, Fisher's relation, that says that gamma is equal to 2 minus eta times nu. And this is not something which is just specific to this model, but it always holds. And there's another relation. So scaling relations are relations between the exponents that don't involve the dimension. Hyperscaling relations are relations that involve both the exponent and the dimension. Like that one. Now, the focus is on these exponents because of their universal quality. So that is to say that they don't depend on the details about how the model has been defined in the first place. For example, instead of talking about the phi to the fourth model with the Laplacian, I could have taken, which only has nearest neighbor interactions, I could have allowed next neighbor interactions, or any finite range interactions. For all those models, nu c will be different, and the amplitudes will be different in these formulas, but these exponents are supposed to be the same.
Nu is nu bar there, right?
And nu is nu bar. Thank you. Not only that, but the phi to the fourth exponents are predicted to be the same as the exponents for the Ising model when n equals 1. And there is a relationship between the phi to the fourth model and the Ising model. If you scale things correctly and let g go to infinity, then these wells will drop down to infinity, and you're basically getting delta function at plus or minus 1 here, or plus or minus something. And so that's what an Ising spin does. It only takes 2 discrete values. And these exponents for the phi to the fourth are expected to be always the same as for the Ising model when n equals 1. When n equals 2, you could, instead of thinking about the phi to the fourth model, think about what's sometimes called the ON model or the n vector model, where the spins are constrained to lie on a sphere, uniform measure on a sphere. In that case, the exponents are expected to be the same as they are for the n equals 2 case of the phi to the fourth model.
Alpha h can be negative.
That's right. Yeah. In fact, we're going to see that it's kind of 0 in a minute in the cases that I'm interested in. So for d greater than 4, this picture is pretty much all been.
Then you have to modify the definition of th.
Yes. So alpha h is sometimes called alpha sing because it's the singular part of the specific heat. So if there's a yeah. So that's true. In our case, it's going to be like this in the theorems that I'm about to say. So for d greater than 4, a lot of this is, almost all of it has been established. The exponents take on mean field values. Gamma equals 1, nu bar equals 1/2, eta equals 0. That was from the early 80s. All right, so that's our problem is how are we going to compute these exponents? The answer is with RG in 4 dimensions. And also, that's for the nearest neighbor model. I'll also say something about what's happening in the long-range model. Okay, but before we get to stating what is the theorem that we want to be talking about for the rest of this course, I want to mention another model that falls into this category, even though it looks different on the face of it. The method of proof, which is used to attack this problem that I'm about to present, is the same. In fact, the theorems are, in a way, proved simultaneously, which is the n equals 0 case. I mean little n. So n is the number of components of the spin, so there's no real, you don't know what it means to take n equals 0, but de Gennes in 1972 argued that the self-avoiding walk model is the n equals 0 case of this n-component spin model by writing the correlation functions or the susceptibility of the spin model with n components in terms of a loop model, where, so it's a stochastic geometric representation of the model in which there are self-avoiding walks and loops. The loops have a factor n associated to them, and if you throw away, if you put n equals 0, that gets rid of the loops and it leaves the walks. So that was useful within physics for understanding self-avoiding walks, because once you understood this problem, then you also understood self-avoiding walks. But from the point of view of mathematics, that left something to be desired. So I want to explain how that can actually be done here. So what is this weakly self-avoiding walk? Take x to be the continuous time simple random walk on ZD. All right, so this is just the nearest think of the nearest neighbor case. So this is a random walk, just like the usual simple random walk, except there's a continuous time, so there's an extra level of randomness, which is the times at which the steps take place are random. So there's an exponential clock associated to every vertex, and when the particle lands on the vertex, that clock is going to go off after an exponential amount of time, say with rate 2d, and then a neighbor of the current position will be chosen at random and independently step to that new position and then continue. So that's what x is. It's the continuous time simple random walk. It has some generator. Let's take q to be the Laplacian, or it could be minus the Laplacian alpha over 2 if you want to consider a long-range walk, which actually I also do. So what that means, that this is the generator, is that if you want to know what's the probability starting from x that your random walk is going to be at position y after time t, that's given by e to the tq, that matrix xy. Right, so this is a self-avoiding walk, or a weakly self-avoiding walk, and so I have to say, how are we going to enforce that avoidance? That's in terms of a random variable associated to x called the self-intersection local time. So up to some fixed time horizon, capital T, what I of t is, it's a random variable. It's a double integral of the indicator function that the walk is at the same place at 2 times s and t. And little s and little t are integrated up to time capital T. So this is a measure of the total amount of time that the walk spends intersecting itself. You can think about it that way. It's self-intersection local time. Now, for g greater than 0, should look familiar. It's like that g up there. We'll define c sub t, which depends also on g, and x, a lattice point x. There's no finite volume approximation needed to define this model. So we're on ZD. It's the expectation with respect to this simple random walk started from 0 of e to the minus g I of t times the indicator that the walk be sitting at the point x at time t. So the walk starts at 0. At time t, I'm forcing it to land at x. And then we're weighting x, capital X, according to how much time it's spent intersecting itself. And the more self-intersection there is, the less that particular capital X is going to contribute to this expectation. Walks are allowed to intersect themselves, and so it's not a strictly self-avoiding walk. Although you can get the strictly self-avoiding walk by taking a limit here as g goes to infinity in the same way that you can get the Ising model from the phi to the fourth model. Pardon me?
What's the element called the new variable?
Yeah, I'm coming to that. Thank you. So in addition to this, I'm also interested in the case when we do not fix the endpoint. So CTG is just the sum over x in ZD of CTGX. And that's just the expectation of e to the minus gi without the indicator. All right, so what is new? Well, there's a two-point function. And the two-point function is g0x of g nu. And now I'm going to put a 0 here that corresponds to little n equals 0. Although there's no little n in this formulation, I still want to record it in that way. And it's the Laplace transform of CT. And I guess there's an x. But for the susceptibility, there'll be no x. So the susceptibility is defined again as the sum over x of the two-point function. And so that's just the Laplace transform of CT. And there's a certain subadditivity property, it's a submultiplicativity actually of this this function C of t that tells you easily that this is behaving like e to some nu c times t. It's behaving exponentially with a negative value of nu c. So there's a subadditivity argument, or submultiplicativity, that tells you that you have exponential behavior of c of t. And so from that, you immediately see, so the sense that this, the meaning of this is that if I take the tth root of ct and let t go to infinity, it will converge to some finite limit, which I'm calling e to the nu c. Now, from this, you see that this is going to be finite if nu is greater than nu c, and it'll be infinite if nu is less than or equal to nu c. So we've got this same kind of phenomena of the susceptibility blowing up as nu decreases to some critical value nu c. And again, there are critical exponents that describe, that are just analogs of all of these ones here. So, well, I don't want to talk about the specific heat in this context, but for chi and the correlation length and for the two-point function, you have this same behavior. So this chi of g and nu 0 will behave like 1 over nu minus nu c to the gamma. These gammas and nus and so on, they do depend on the number of components. Okay, so this gamma will not be necessarily the same as those gammas over there. Etc. So why are these related? Well, there's an interesting story about that, which I'm not going to enter into in detail in these lectures, but I want to give you just a hint because I find it fascinating of the relationship between this model, which is just defined in terms of random walk and self-intersection local time, and the phi to the fourth model, which is defined in terms of spins. They look very different. How are they connected? So I already mentioned that de Gennes had an idea about what that relation would be. That's not the route that I'm going to be following here. There was independently, some years later, 1980, Parisi and Surla and McCain independently came up with a different way of understanding n equals 0 components, not as a 0 component spin, but as a combination of, in our case, it's going to be a 2 component spin and a minus 2 component spin. And so together they add up to 0. And so the minus comes from having a fermion field. So I'm going to put this in brackets here because this is just a bit of an aside, just to give a flavor as to how there could possibly be some relationship between these two models, which at the moment look rather different from each other. So I'm just going to write a formula which makes the connection. I'm not going to try to justify the formula or prove it to you or anything like that. So this is on lambda n. I could, of course, define this continuous time simple random walk on the torus instead of on ZD and define the 2-point function and the susceptibility and finite volume. And that's what I want to do here. So I'm going to be talking about the weakly self-avoiding walk on lambda. And this will be impressionistic, but it's a beautiful formula. So the 2-point function, this is for the self-avoiding walk, is given by an integral over c to the lambda, so the complex, e to the minus the sum over x in lambda of g tau x squared plus nu tau x plus tau delta x phi 0 bar phi x, not var phi. This is a complex field. So phi is a complex field associated to each point in lambda. There's a complex number phi x. So this is the complex conjugate up here. And what is tau? Yeah, so I want to say what everything in this formula is. There's a tau and a tau delta. So tau x is equal to phi x bar plus 1 over 2 pi I. You might recognize that 1 over 2 pi I from Horst's lecture. D phi x wedge d phi x bar. And tau delta x is equal to phi x minus Laplacian phi x plus 1 over 2 pi I d phi x wedge minus Laplacian d phi x bar. So d phi is a one form, and so this is a 0 form plus a 2 form, and this is a 0 form plus a 2 form. And you know, what you might have noticed in this formula is that I didn't write any measure for that integral. And instead, the measure is sitting up in the exponent, which is not its usual location. So you have to construct the measure from this formula by integrating, by expanding out all of the differentials. So you just do a formal power series expansion of this integrand in the d phis and the d phi bars. And you use the anti-commuting property of the wedge product to tell you that that series will actually terminate. And you keep only the terms which are of the form product over x, d phi x bar, d phi x. And then you write that in terms of real variables and do a Lebesgue integral. So that's the meaning of the right-hand side. It went by a little bit quickly, but anyway, there is a meaning for that. And it's equal to this two-point function for the weakly self-avoiding walk on the discrete torus. Now, when it's written this way, well, maybe I'll just say some terminology that this pair phi x and phi x bar is a boson field, and d phi x bar is a fermion field. You can also write this in terms of Grassmann variables, but it's convenient to represent the Grassmann variables in terms of differentials, and then this just becomes ordinary integration. You don't need Grassmann integration. But this two-component boson field shows up here in tau as phi squared, and there's a tau squared, so there's a phi to the fourth. So there's a g phi to the fourth in this term, there's a new phi squared in that term, and so you see that at least there's some kind of correspondence now between the weakly self-avoiding walk and the phi to the fourth model. All right, so I close the parentheses there because I'm not going to be returning to this topic, but I leave it at that. All right, so I'm going to state a couple of theorems. So theorem 1, let d equal 4. I'm talking about the nearest neighbor model. So that means that that matrix M that I started with is just minus Laplacian, usual Laplacian on the torus. Let n be 0 or 1 or 2 or 3, etc., any non-negative integer, including n equals 0. So the n equals 0 case means the weakly self-avoiding walk. Let L be large, and let G be small. So then there exists a critical value, nu c, which depends on G and it depends on N, such that these critical exponent formulas here that I wrote down, they're all verified. So chi, the susceptibility, so I'm writing now nu as nu c plus t. So t is a positive number, which is, I'm interested in the limit as t goes down to 0. That means I'm going to be approaching the critical point. Behaves like some amplitude, and this means asymptotic formula, that the ratio of left and right hand sides converges to 1. Some amplitude gn, 1 over t times the log of t to the power n plus 2 over n plus 8. This is as t goes down to 0. So that's a statement that gamma equals 1. Gamma is the power here on t, but this is nu minus nu c. But there's a logarithmic correction in 4 dimensions. And this is a universal power here. The correlation length behaves like the square root of the susceptibility. 2-point function at the critical point behaves like some other amplitude, 1 over x squared. So that x squared is x to the d minus 2 plus eta, with d equals 4 and eta equals 0. There's no log correction for that. And finally, the specific heat which I only define for n greater than or equal to 1, the specific heat has interesting behavior as a function of n. So nu c plus t, and it has some other amplitude. And then what happens depends on the number of components of the spin field. So if it's less than 4, then there's a logarithmic divergence with a power 4 minus n over n plus 8. If it's equal to 4, you have a log-log. And if the number of components is greater than 4, then it doesn't diverge at all. So this is a combination of work by the people that I mentioned earlier. So joint work with David Brydges and Roland Bauerschmidt and Alex Tomberg, Ben Wallace. Some of these results were proved in the mid-'80s for the case of n equals 1. So for n equals 1, Antti Kupiainen and Krzysztof Gawecki proved this behavior for the critical 2-point function. Takashi Hara in his PhD thesis proved behavior of the susceptibility for n equals 1, and also the correlation length, so-called true correlation length, the one that gives you the exponential decay of the 2-point function away from the critical point. So it means that there exists a g naught greater than 0 such that for all g less than or equal to g naught, these results hold.
G naught depends on n?
Probably, yeah. Yeah. Right. So notice, though, that the exponents don't depend on g. So none of these exponents depend on g. The amplitudes, of course, they do. But the exponents should be the same for all values of g. But our analysis is restricted to small g. And if I can get ahead of myself a little bit, which maybe is OK because of, if you've heard Antti's lectures, you know that there's a renormalization group fixed point, which is underlying all of this renormalization group analysis. There's some kind of an RG map and an RG fixed point. And in this case, the fixed point is g equals 0. And our work is a local analysis near the fixed point. And so we need to take g small in order to be close to that fixed point.
Can I ask now?
Yes?
So you mentioned L large, but does anything depend on L in the end?
No. Well, some of these amplitudes might depend on L. No. Nothing depends on L. Yeah. Any other questions? Yes?
So when we define this step-avoiding walk, this CTG looks like the total mass at time t.
It looks like the Kondo mass?
Total mass.
Total mass.
So wouldn't it be natural to reweight this measure so that the total mass is always 1?
Sure. Yeah. So if you wanted to define, if you wanted to ask yourself, for example, how far does this weakly self-avoiding walk travel in time t typically, then you would define a measure which is you would normalize it by this CTG. Yeah, that's true. If you like, you can think about this as a kind of a generating function version of that finite t question. We're studying the Laplace transform of the finite t object. Okay, so in the time that's left, I want to say one more thing, which is about epsilon expansion. So if you remember Anti's lectures, he talked about that, the epsilon expansion in physics, where you, Wilson and Fisher had this amazing idea of saying, well, let's look at the dimension line here. There's this critical dimension 4, and then you have these other dimensions that you might be interested in down below, especially 3. And if you understand what's going on in dimension 4, maybe you can understand lower dimensions by perturbing around dimension 4. So you take d to be 4 minus epsilon and try to promote your knowledge from what's going on in d equals 4 to dimensions below 4. But of course, this raises some questions as like what does it mean to talk about 3.99 dimensions, for example? We don't have a model. We don't know how to define the model in that context. So you can do things like Anti described a little bit to try to get around that. But anyway, it's somewhat mysterious. So this is for the nearest neighbor case. So in the long range case, there's a way of mimicking this, which is, from the mathematical point of view, more realistic, which is to work with the long range model and now choose, so here's dimension 4, dimension 3, dimension 2, dimension 1. Don't try to move take D near DC. Try to take DC near D. So, you set things up so that the critical dimension is sitting, for example, here. And you don't actually have to define a model within the critical dimension. It's somehow, you work in dimension 3, but you want to arrange things in such a way that, the critical dimension ought to be a little bit bigger than 3. And in the long-range model, the critical dimension is 2 alpha. So, a hand-waving way of understanding why the critical dimension is 2 alpha is the following. So how would you understand that 4 dimensions is critical for simple random walk? You can do it like this. You can say that Brownian motion, which is the scaling limit of simple random walk, is a 2-dimensional object. Okay, the paths of Brownian motion are 2-dimensional. Two 2-dimensional objects generically will not intersect themselves in more than 4 dimensions. So if you ask the random walk, not to intersect itself and to be a self-avoiding walk, it will say, well, if I'm in more than 4 dimensions, I didn't really want to intersect myself anyway, and so I'm going to behave the same way, with or without the constraint. So if you try to make that same kind of argument for the long-range walk, the role of Brownian motion is played by an alpha-stable process. And an alpha-stable process has paths of dimension alpha. And so 2 alpha-dimensional objects generically won't intersect each other in dimensions higher than 2 alpha. So you could imagine that the long-range self-avoiding walk is going to behave like long-range simple random walk in dimensions more than 2 alpha. Anyway, the upper critical dimension is 2 alpha, and so what you want to do is just arrange that 2 alpha be a little bit bigger than the d that you're interested in. So if you want to take d equals 3, then you'll take alpha to be 1/2 of d plus epsilon for small epsilon. And now I'll finish by stating a theorem here that deals with this context. So theorem 2, let d equal 1 or 2 or 3. I'm now working with the long-range model. Take epsilon greater than 0 to be small. take L to be large, take alpha to be 1/2 of d plus epsilon for the d that you picked between either 1 or 2 or 3, and a small epsilon. Let n be 0 or 1 or 2, etc. So the case of n equals 0 is the long-range weakly self-avoiding walk. The case of n equals 1, 2, and 3 is the long-range phi to the 4th model. Then for g in some interval c epsilon, c prime epsilon. So epsilon is fixed here and small, and I'm looking at a small interval of g's which are around epsilon. There exists a critical value such that, well, I'm not going to write out all of those formulas again. The time is getting short here, but I'll just say what the exponents are. So gamma was the exponent that tells you how the susceptibility is diverging as t goes to 0, or as nu approaches nu c. And it has the form 1 plus n plus 2 over n plus 8 epsilon over alpha plus order epsilon squared. G0x at the critical value behaves like 1 over x minus y to the d minus alpha. No, there's no y here, just x. And, well, one more. I'll just write down the case of the specific heat for n greater than or equal to 1 for number of components less than 4. It's equal to 4 minus n over n plus 8 epsilon over alpha plus order epsilon squared. And there are some weaker statements about what happens for the other values of n that I won't mention now. So, you see the n plus 2 over n plus 8. What's happened is this logarithm, it turns into a power. There's this epsilon over alpha that shows up in there as well. For the 2-point function, this decay, interestingly, is the same as the decay above the critical point. So it's the same as the decay for the non-interacting model, the Gaussian model, with the fractional power of the Laplacian has this decay for its Green's function. It doesn't change as you go below the critical point. There's something very interesting that's going on there that has been extensively studied in the physics literature recently, in particular by Slava Rychkov, how that, as alpha gets small enough, this power changes. Okay, so the proof of Theorem 1 and Theorem 2 are pretty much the same in many respects. A difference here is that there is a non-Gaussian fixed point. So there's some fixed point of order epsilon, which Antti mentioned. And this restriction on G is requiring that we're close enough to that fixed point that we're able to carry out the local analysis which is involved. The method of proof doesn't really care whether those fermions are present or not. There's a certain sort of pre-processing that you have to do with the fermions that involves the Graham bound that Vieri mentioned in his talk. But by and large, there's like a general approach to proving these theorems, which is what I will talk about over the next 3 hours. So thank you very much.